Good evening, sir.
Yeah, good evening, everyone. So let's just wait for 2 minutes and then we can start. So have
Okay,
you
sir.
have you gone through the week two content, like the lectures and the material of week two?
Yes, sir.
Okay. So we'll do the same thing like last week. Like we did a theory session, right? So we covered all the theory concepts of week two. That's what we will do in this session. So we did week one last week. So week two I'll cover today. We'll try to understand all the full pass, that is the forward pass and the backward pass in the ANN, and we'll see. We'll discuss about the gradient descent algorithm as well. That is also something I think we talked in brief about last week. So this week we'll take it up in more detail. So yeah, let's wait for 2 more minutes and then we can begin the session.
Okay, sir.
Yeah. In the meantime, I'll just share the screen. So just tell me if you can see the PPT in a minute. Yeah, can you see the PPT?
Yes, sir.
Okay. Eight a.m. No, no, we only have 8 p.m. Friday and Saturday at 8 p.m. Okay, I think we can start the session now. So others will also join in. So I'll give a quick recap of what we did and then we can begin with today's topics. So in week one, basically we try to understand the motivation for neural networks, right? So we try to understand what neural networks are and why do we use neural networks and everything. So all that I think we understood, and how neural networks actually evolved from the basic ML to perceptron to sigmoid neurons and to a fully connected network like this, right? So these are the structures which we basically saw last week, where we had this input, then we had some hidden layers, right, and then we have a output. So that is basically what we tried to see last week, and I think with that we had a clear idea of how data flows and what basically different activation functions and different weights and biases do to the data. That's what we understood, right? So in this week basically we'll continue that and we'll try to understand even further on how neural networks actually work, how the learning part happens in a neural network, and how basically all the major concepts of neural networks actually come together and they actually give us the outputs that we expect, right? So before we start with that, we'll try to just revise one quick topic that we have covered last week, but Sir has covered it in the sessions of this week also. So this topic is called as the universal approximation theorem. So what this universal approximation theorem says is very simple, that any function, okay, any function in the sense any learning that you want to do for any data, a neural network will always be able to do that. Okay. So for example, if I have an input like this, like I have three features, x1, x2, and x3, and I have the label y, and I know the actual function that is there, I know that y is equal to 3.5 by 2 into root x1 into x1 plus 3.5 by under root 2 sine x2, okay, plus 1.5 x3. Now suppose this is actually a relation between x and y. This is a real relation. If I build a very complicated neural network with a lot of hidden layers and a lot of neurons, I will be able to learn this and I will be able to predict this actual relation as well. And that's the main idea, right? So whatever, how complementary, how complicated your real relations and real functions are, if you build a deep neural network, you can always learn that function and you can always approximate that function. That's the idea. Okay. So that's what this graph also shows you, that you have two things. One is the actual function that is there, and the second is the neural network. So you can see the actual function is pretty complicated. It's not a very simple curve. It is topsy-turvy like this, right? But the neural network also, if you build a deep neural network, this network will also approximate this function and it will actually learn this function pretty well. That's the idea. Right? This is very simple. Just to understand that why we are actually doing deep learning, that because in deep learning, whatever the function is, even if machine learning fails, deep learning will not fail. Deep learning will still give us the actual output. So I hope that is clear so far. Any question on this? This is just to give you a motivation. That's all. Right? Yeah. Okay.
But will it not go for overfitting?
Yeah, overfitting and all will happen. That we have to solve. But the idea is that it will learn the function, no matter how complicated it is. Okay. Overfitting and all will be there. That we will solve. We have methods to solve that. We will see more of that in week 3. But the idea is that no matter how complicated the real data is, the network will be able to approximate it. It will be able to estimate it. That's the idea. Okay.
Okay.
Yeah. Okay, so now that was just a motivation thing. Now let's come to the actual week 2. So in week 2, we'll start with the first discussion, that is the loss functions. And I think this is something that you have seen in your machine learning course also, right? MLT course, you must have done it in detail. So I'll give you a quick recap of these functions as well. So basically, what is a loss function? So can somebody tell me what is a loss function? Like in just in a definition, a simple thing. What does a loss function actually do? Why do we need it? What is the use of a loss function? Can someone tell me?
It's the difference between the target and the predicted value.
Correct. But what is the use of it? Like, why do we need it?
It's to update the
Sir,
weights and
Yeah. So
come
basically, if
back,
I want to
minimize
say
that.
simply, if
Minimize.
yeah, that is correct. If I want to say simply, loss function basically gives you an idea of how good your model is. Is this correct?
yes, sir.
Yeah, because if my loss function is less, that means my model is doing a good job. And if my loss function is high, that means the model is doing a bad job. Right? And how do you get these high and low values? That is by using some mathematical formulas like this. That we'll come to later on. But the main idea is a loss function in a neural network always helps you to estimate whether your model is good or not. So just like in ML we had loss functions, the same loss functions will happen in DL also. In neural networks also you will have the same functions. Right? So I think two loss functions that you already know are MSE, which is mean squared error, and the cross entropy loss. So let's try to just quickly have a recap of them. So MSE is pretty simple. So can you tell me what is MSE used for? Is it used for regression or is it used for classification?
Regression.
Yeah.
Regression.
So regression, right? So MSE is used for regression. That we know. What does MSE do? The same thing, just like the name. It takes the mean of the squared error. So what is the squared error? Simply like suppose you have regression, you are predicting prices, right? Prices of house. So suppose this is the model you're doing. This is house 1, this is house 2. My house 1 has an actual price of 5 and the predicted price that my model gives me is 4.5. Similarly, my house, or let's just take integer, let's take 4. Similarly, my house 2 has a price of 4 and the predicted model gives me a price of 6. Alright, so how do I calculate the mean squared error? First, I just take the error, which is basically the difference of the actual and the predicted. Right? So this is going to be 5 minus 4. Okay, and this is going to be 6 minus 4. Right? Sorry, 4 minus 6. So it's going to be 1 and this is going to be minus 2. Right? Simple. Then what I'll do is I'll take the square of it. So let's take the square of it. The square of this is 1. The square of this is 4. Right? And finally what I'll do is I'll take the mean of this. So what is the mean of this? 1 plus 4 by 2, which is 5 by 2, which is 2.5. So this is your mean squared error, which is pretty high. And you can also see that if I actually see my actual data, I have 5 and 4 and I have 4 and 6, which means there are some differences, right? They are not very close. The actual and the predictions are not very close, and that's why I'm getting an error of 2.5, which is pretty high, right? So this is, I think, something we have seen earlier also, the same thing. So you just take the difference of the errors, then you square them and you take the mean. If the error is high, that means the actual observation and the predicted observation is pretty different. And if the error is low, that means they are similar. That means the model is doing a good job, right? So I think someone raised the hand. So yeah, you can go ahead.
Sir, we do have a mean absolute error also, right?
Yeah. So basically, the idea is that this is the most used one. That's why I've just taken this as an example. But you have MAE also. So in that, you just
Okay.
instead of squaring it, you just take the absolute value, right? You take this
Okay.
absolute value, right? Yeah. Even you have RMSE also, root mean squared error, where basically you just take the square root of this, right, to nullify the squared effect, because we have squared the values here, right? So to nullify the squared effect,
Yeah.
we just take a root of it. That is also there. So there are many metrics, but the base metric for regression is mean squared error. Based on this, you can change it and make different metrics. That is up to you. Okay. Yeah, so I think this was a simple idea of mean squared error. So I think everyone knows this. So I'll move on from this now. So let's move to cross entropy. Now, cross entropy, can someone again tell me, is this for regression or for classification?
Classification.
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 Yeah, and this classic cross entropy is something we'll be working with more as well, because in this course in deep learning we'll mostly talk about classification. Regression can also be done using deep learning, but classification is actually which is more actually famous. The hot topic of deep learning is classification, so that's what we'll be discussing more. So pay attention to this for sure. So what happens in cross? I'll just change the color. Yeah. So what happens in cross entropy is it is a classification loss function, and we already know that in classification you are not going to see data like this. This is not something what you're going to see, right? So what you're going to actually see in classification is data like ones and zeros, which are the classes, right? So my actual class can be one and my prediction can be zero. My actual class can be one, my prediction can also be one, and similarly for the other classes as well. So I'll have binary values, right? Zeros and ones. So this is one value and this is one value of the classes. So what does cross entropy loss do? Cross entropy loss, so I'll just take a new page and maybe write on that. A simple formula for cross entropy loss is this: minus 1 to c ln y hat ln y hat. That's the simple formula. Now let me try to explain you what this formula does. This y hat is simply the probability of prediction. Now, if you remember last week, we discussed about sigmoid neuron, right? And we discussed that sigmoid neuron gives me an output of 0 to 1. So it basically gives me a probability of a class, right? This is something we discussed last week. Same thing. So for example, you are using a neural network here and it has a sigmoid neuron here and you get some probability, and that probability is called as y hat, right? So for example, it can be 0.5. So if the probability is 0.5, my cross entropy loss will become simply 0.5 ln 0.5. No, sorry, small mistake here. Just a minute. This was y, not y hat. So I'll explain the difference. So ln 0.5 I think is clear to everyone. This is simply the loss, right, of the probability. I'll just take the logarithm of the probability, and ahead of that logarithm, I will multiply it with the actual class label. So for example, actually with the training data, I know that this was belonging to class 0. So basically, I'll just multiply it with 0. That's all, right? So my cross entropy loss for this particular term becomes 0. In the same way, now if we take class 1, so if the class is 1 and my y hat is say 0.7, this loss will become 1 into ln of 0.7, which is simply ln of 0.7, and this will be some value which you can compute, right? So the idea is very simple. My cross entropy loss is basically penalizing the probabilities using this logarithmic function. That's all, right? Why it is doing that? Because log basically helps smoothen the exponent, because this probability that you're getting, this is through a sigmoid function, which is an exponent, right? So this log is basically to smoothen that exponential factor. There are other reasons also, we'll come to that later because it might be out of scope of this current session. But the idea is we simply take the logarithm of the correct class and we multiply it with the probability. We take the logarithm of the probability of the correct class and then we multiply the class with the class label. So whatever classes were 0, which were the other classes, the loss will become simply 0 for that. And whatever class which was correct, the correct class, the loss will be taken for that correct class because it gets multiplied with 1. That's the idea. Okay. So any question on this? Is this clear so far?
So here, why does the sum go from minus 1 to c?
C is the number of classes. So it is for all the classes. No, it's not minus 1. Sorry, it is 1. By mistake. This is 1.
Okay.
1 to C. Yeah. Sorry for that. It's 1 to C. Okay. So all the classes. So C is the number of classes. C is the total classes.
So in the formula we have minus, right? Minus sign.
I think that is a typo. My mistake.
No, but I have seen like maybe a minus sign we have, I guess.
See, we can also take the minus sign. It is not a tie, like it can also be taken, because the idea is, see, whenever you take the ln, right, the ln function, it can give you negative values. So if you want to measure the log in a positive value, you can take the minus of it. Like for example, like suppose I say ln of 0.5, suppose I'm not sure what this is minus 2.7. So I'll tell my loss is minus 2.7. But I'm actually just interested in this value, right? I'm not interested in the sign. I just want to see if the deviation is large or small, right? So I can take a minus of this and I can just take 2.7. That is also something I can do. Right? So both are correct. You can take both. Right? But see, the problem was I was writing the minus here. This is not minus 1, right? That was there. You can write the minus here. This is okay. Okay? So the idea is whenever you are taking a loss function, you don't care about the sign. What you care about actually is the value. How much is the loss, right? How much is the deviation? That's what I want to get at. Yeah. So either I just look at the value or maybe you take a minus of minus to make it positive, right? That you can even do it like this. Like even this is a correct formula. If you take this, if you take this absolute value. That's also correct, right? Simply just remove the minus with the absolute. You can do all these variations. Every textbook or every paper has a different variation of it. But the idea is you just need to measure the deviation, not the sign. Okay, so I'll simply write don't use sign. In our course, we will give you whatever entropy formula has to be used. We'll give you. Suppose mostly we'll use this minus thing, where basically we'll ignore the sign, right? We'll just take the positive value of it. Okay, that's the thing. So even if you see this variation where you have an absolute value on cross entropy, that is also correct. It's not wrong. Yeah. Any questions on this so far? Is the idea clear?
Yes, sir.
Yes, sir.
Okay. Okay. So I think that is pretty good. So we are done with this. Okay. So basically now just to recap quickly, what we have done so far is just a minute. Yeah. So what we have done so far is we have talked about neural networks, right? We have talked about sigmoid neurons and different activation functions, and we have also talked about loss functions, which will basically be the deviations, right? And if the loss is high, that means my model is bad. If my loss is low, that means my model is good. This is what we have discussed so far. Now the idea is let's talk about the actual learning, right? So let's again go back to this picture of a neural network. Let's assume there are two neurons in this layer and just one output neuron. So let's go here, and this is a simple sigmoid, and it gives me some probability. Right, this is something we know. This is the input, so we can call it x1, x2, two features in the input. This is the output. So this is the output, and we just have a sigmoid neuron at the output, and we get a probability. So this is the probability. This simple network we are talking about. Okay. Now, if you remember, we also have these weights here, right? And we also have biases as well, b1 and b2. So whenever we are going from one neuron to the other, we have weights and biases that are involved, right? So basically, if you remember the perceptron formula, we had this wx plus b, right? Where w are all the weights and b is the bias, which we are adding to all the neurons. Now, basically, tell me one thing. Suppose when we learn through this network, when we first pass our inputs, right? And we get this y hat, the final probability in this forward pass, we get this y hat is equal to say 0.7. So our loss is going to be simply as minus ln of 0.7, which is the cross entropy loss, right? And suppose this is, let's assume this is 3.5. So this loss is high, right? So if I get this high loss, what do I do? What is something I should do? From your ideas of machine learning, can you tell me what should we do if the loss is very high? How do we?
Minimize the
We
loss.
can,
Minimize the
Yes,
loss.
minimize the loss, right? So if the loss is high, we'll want to minimize this loss. Now to minimize the loss, let's assume, let's take the formula, the mathematical approach. Okay, I'll take a new slide again. So what we have has our input. Let's call the input as x. Okay, so this contains all, these are matrices. So all the x1, x2, x another. I'm just simplifying it with 1x. All the weights are w and all the biases are b. Okay, these are simple notations we're taking. So we know initially what we do is we do wx plus v. Okay, simple perceptron rules we are taking. And then basically we pass this entire thing through a sigmoid neuron, right? And then on this we basically get an output probability, and on that out probability we basically take the this cross entropy loss. So I think we can also call this simply as y hat, right? Instead of output, let's call this as y hat. Okay, we take the loss on this, and what we want to do is we want to minimize this loss. Can you tell me, to minimize this loss, what can we do? What can we change to minimize this loss?
You can change the weights.
Exactly, right? Because obviously, if you see the sigmoid, you need, because you need a probability, right, and the output. So you have to have the sigmoid. You can't do anything of the sigmoid. This has to be there. This will be there also. This is the input, right? You can't change the input. We can't change the input, right, to modify the loss. The input will be same. We have to learn the input, all right? What can be actually changed is this and this. These are variables, right? Because weights can be anything, biases can be anything. These can be changed. So what I'm trying to say is, if I write that this loss, which is the cross entropy loss, is a function of w and b. Is this correct?
Yes, sir.
It is correct, right? Because w and b
yes, sir.
values are determining what this loss is. This is fixed and this is fixed. These have no role, right? What is variable is this, and what is variable is this. So I can change this. So basically, what I can say is, to minimize this loss, I need to update w and b. So basically, I need to find those w and b which will actually minimize this loss, right? That's the idea. To illustrate this, let me take a simple diagram here. So yeah, so suppose we have, let's just assume the loss is a function of w and b right now, which it is. Okay, so this is my b, This is my W, right? So I have different values of B and W. So suppose let's take this as 1, 2, and 3, and let's take this as 4, 5, and 6. These are different values of W and B. And what I'm going to plot is I'm going to plot the loss. I'm going to plot the loss function as a function of different values of W and B. So for the first combination, I get the loss is somewhere here. For the second combination, I get the loss is somewhere here. And for the third combination, I get the loss is somewhere here, right? So this is my loss function. This entire thing is my loss function. Okay. So can you tell me, this is point A, this is point B, and this is point C. At which point of A, B, and C am I actually wanting to go to?
Between
B.
2 and 3, B and C.
Yeah, because B and C both minimize this loss function, right? So at any of this
Local
point B
minimum.
and C is what I want to go to, right? So can you tell me from mathematics what are these points called of a function?
Local minimum.
Local minima.
Yeah, so local
Local
minima.
Minima.
Yeah, correct. So these are called as local minima. And if I have a simple function like this, which just has one minimum here, what is this called?
Global
Global
minimum.
minimum.
The global
Global
minimum,
minimum.
right?
Global minimum.
So global minima. So basically what I want to do is I want to actually go to a global minima. Because if you remember from mathematics, local minimas might not be the global minima, right? Because if you
Yes.
see this function, this is a local minima, this is a local minima, but this is a global minima, right? I want to go here. I want to minimize the loss, right? I don't want to go into local minimas. I want to go into the point which is the global minima, right? So basically what I want to do is I want to learn an algorithm which will help me converge into the global minima of the loss function, right? Now tell me one thing. What do you think? Like, how should we like the model? If I have an algorithm, the algorithm can go get stuck here also, right? But I don't want to get stuck here. I want to get stuck here in the actual global minimum. So how is there a technique on how we can escape this?
No, sir.
No, right? Because minima is minima. You can't change the function. But one hack which you can think of is if my loss function looks like this, then it's good, right? If the loss function itself doesn't have a global minima, then I can local minima, then I can reach the global easily, isn't it?
Yes.
Like instead of
Yes,
taking
sir.
a loss function which is complicated like this, if I take a simple loss function like this, that's going to do the job, right? There is no local minima. Where will it get stuck? There is no local at all. There is only one global minima which is here, and the function will go here straight away, right? So again, if you remember from mathematics or MLF, I think this was covered. These types of functions are called as convex functions.
Convex functions.
Convex.
So what are convex functions? Which are basically having only one minima, which is the global minimum. There is no local minima here, right?
Yes.
So the idea is, why do we actually choose these loss functions for machine deep learning? Is because both of these loss functions are convex in nature. If you see simply, this is a parabola, right? This is a squared function. Simply a squared function, right? And we have mean squared error. So this is square function. So this is
Yes.
convex. In the same way, if you see the cross entropy, that is also a convex function. Okay. And there are some one or two other loss functions as well, which we use in deep learning. All of these loss functions are convex functions. I think someone raised the hand. So just give me a minute. Yeah, Viral, you can. No, I think Karthikeyan has it. Yeah, Karthikeyan, you can go ahead.
Actually, but the loss function, choosing a loss function is not in our hand, right? The loss happens.
No, it is in our hand only. The researchers who and like not invented. I'm sorry. The researchers
Because
who
based on the
discovered
loss, we change the weight.
yeah. So
But
basically,
how do we specify my my sigmoid wx plus b has to follow this loss? Can you just briefly touch upon and then proceed with your session?
see, if you remember, I'll tell you with an example. You remember from machine learning, there was an algorithm called as KNN, right? K nearest neighbors.
Yeah.
So basically,
Yes, sir.
that we had to choose the K, right? When we wrote the code for it, or when we understood the theory for it, the idea was you choose the K. You tell how many neighbors you want the algorithm to see.
Yeah, we start with and then we move on. Yeah.
Then you can optimize, right, later on. But you start with something. In the
Yeah, we
same way,
start,
when you
of course.
in the same way when you build a neural network, you start with something, and then you move on and do updates, which will basically give you the optimal result. Like basically, suppose I am solving a simple problem. I will decide that I have a 3-layer network. This is up to me. In the first layer, I have 50 inputs. Second layer, I have 100 hidden layers. And the final layer, I have one output. Here, I have a sigmoid. Here, I might have a ReLU. Here, I don't have anything because this is just the input. Right? And my loss will be MSE. All this is decided by me. Okay. Then I will update the parameters with these weights and biases, and I'll see when how I can minimize this MSE. If I'm able to minimize the MSE with this setup, well and good. If I'm not able to minimize MSE with this setup, I will change the setup. Like maybe suppose I'll change this into sigmoid, right? Or maybe I'll change this into 10 neurons instead of 100. So I'll do these experimentations. It is up the most difficult thing in deep learning is to design your network. What
No,
is
no.
the actual network?
MSE is okay. Mean squared
Yeah,
itself
this
is a
one.
convex function.
Yes,
You mean to
because
say that that
see,
itself is a convex because
correct,
it is
correct,
the
correct.
square.
It is a convex
Oh,
function.
okay.
That's why it has been chosen, right, from the other functions because it is a convex function.
Yeah.
Because
Thank
if
you.
you, yeah, because see, this is MSE, right? MSE is what a squared function, so x square. It's like x square. And what is x square? A parabola, right? Like this. And this parabola is always convex. So similarly, when you plot the MSE, it's also always convex. Okay. So that's the idea. Whenever we go about loss functions, we always choose functions that are convex. Because if we don't have convex functions, we cannot minimize them. And our algorithms will get stuck in local minimas, right? And we'll never be able to minimize the loss function. It will get same. You'll get the same loss on every iteration. So you have to make sure that you minimize it, and that is how you actually choose a function which is having a global minimum. So that is a convex function, right?
That log is also convex, no? Log
Yeah, so if you see cross entropy losses diagram, you will find it out that it is a little difficult to explain. Like MSE is pretty simple; it's just a squared function, right? This cross entropy is slightly difficult to plot here, but it's also a convex function. You can see the diagram of cross entropy. Like you can use that software called GeoGebra. I think in maths you must have done that. So you can plot the cross entropy function, and you can see that that is also a convex function. Okay.
right.
Yeah. So I'll not draw because that is slightly difficult to draw in hand cross entropy, but you can see it online, a figure on that. Okay. This one was easy to draw, of course, because it's a squared function, right? This one is pretty easy to plot.
So may you explain cross entropy once? Like I
Can
joined
you
a bit
repeat
late.
once again? Voice was breaking.
Cross entropy. Could you please repeat cross entropy once?
Yeah, sure. Like the formula of cross entropy, like how it works. That one.
Yes, sir. Yes, sir. Yes,
Yeah,
sir.
sure. So I'll again write it for you. So I'll create a new slide here.
Yeah, I joined a bit back, so a bit late, so that's why.
No issues, no issues. So see, in cross entropy, we have this formula minus summation I is equal to 1 to C ln y hat multiplied by y. So what this is simply, I think the summation is what? All the classes, right? So basically, if we have C classes in the network, we do a summation over all the C classes. For every class, what we do is, we multiply this y, which is the true label. So I think you remember, right? In classification, we have labels, zeros and ones, the
Yes,
classes, right? So we have the true label, which can either be 0 or 1. And we have this y hat, which is basically the probability of correct class, which is predicted by the network. So if you remember in neural network, we have sigmoid, right? Which gives us a probability in the end.
Yes.
So this is that sigmoid probability, which we have. So basically, for example, if we say that our final sigmoid has predicted the probability of the class being 0.7 and my actual label is 0, what is the cross entropy loss in that case? Can you tell me that?
It would become 0.
0, right? Because it is 0 ln 0.7, which is 0. Straight away a 0, right? So this is 0. But if it is actually my actual class, like that this y is equal to 1 and alpha is equal to 0.7, then what will happen?
So 1 into
Yeah, so basically 1 into ln of
0.7.
which is ln of 0.7, and you will take a minus here because ln gives you a negative output and we just want to see the magnitude of the loss, right? So we'll take this minus sign. Got it?
Yes, sir. Yeah, got it, sir. Thank you so much.
Correct. Yeah. And we'll basically compute it over all the classes like this, and we'll take the summation, right, over all the classes. That's why we have the summation.
Okay.
See, I'll tell you one simple hack. When you are doing classification, like for example, I know that the true label is dog. So I have 3 classes, right, which is dog, cat, and monkey. And I know my label is dog. So for my dog, this dog will become 1, this cat will become 0, and this monkey will become 0, right? Correct, right? Because if dog is my label, the others will become 0 because I know the label is dog. When I'm training my data, I know, right? I have x's and y's with me in my training data. So I have this label that is dog. So in the cross entropy, you will only compute the entropy for dog, right? In that case, because for this and this will become 0. So in the end, you're just going to compute this dog into ln of dog. That's all, right? So basically, the idea is in cross entropy, you don't even actually need to do any summation. You can simply do it as, you can call it in ln of y hat for the correct class. So whatever is the correct class which is given in your training data, you just take a logarithm of the probability of that, and simple thing you get. Because all the others become 0 because you have this y here which is sitting there, right? And which is 0 for all the other classes.
Yeah.
Right? So you only take the loss of the correct class in all the iterations. Okay?
True, sir.
Yeah. So whenever you're solving a numerical, like in your GAs or and your quizzes, and whenever you're solving a numerical, you can take this approach. That will help you to simplify because the rest everything is 0 as it is. So you don't even have to calculate those things, right? So whatever is the correct class, just calculate the loss for that, and that will give you the solution. Okay.
Okay. Thank you.
Yeah. Okay. So any other questions so far? So we have completed the idea of loss functions and global minima and local minima. Now we'll move to gradient descent now. Like how do we actually minimize the loss? So till then, any other questions? Otherwise, I can start with gradient descent after this. Can I start with descent? Yeah.
Yes,
Okay.
sir.
Okay, so coming back once again for a quick 1 minute recap, that what we decided was we understood that this loss function is a function of the weight and bias because rest everything is a constant. So basically what we now need to do is we need to achieve the global minima of the loss function. We need to minimize the loss function, and that we will do using a technique called as gradient descent. Right. So let me just erase all this here so that we can have some space to write. Okay, so gradient descent is very simple, and I'm sure you have seen it before as well. So it will be a good recap of the concept. So what does gradient descent do? Gradient descent is just a technique that will basically help us to achieve the minimum of the loss function, right? So for example, this is our loss function. If we start here, like if our loss is here in the beginning, what gradient descent will do is it will help us slowly converge to this minimum. That's what we want to do, right? How will it help us converge? Using the simple rule. So I'll write it for you. So the rule is simple. In every iteration, suppose we start with iteration 1, right? Iteration 0 is a beginning, right? So we started with iteration 0. So at iteration 1, the weight at iteration 1 will be equal to the weight at iteration 0 minus a constant. I'll come to this constant, what it is in a minute, times the gradient of the loss function at iteration 0. Okay. So the simple thing, let me now try to explain you what actually this does. So again, coming back to this figure, I'm here, right? At iteration w equal to 0, I'm here in the loss function, and I know I need to move to this direction, right? There's something I know. So if you remember simply derivative. So this is a derivative, right? Gradient is what? Gradient is simply a derivative, right? So this is a derivative. What is a derivative? Can someone tell me what does a derivative do?
Rate of change.
Rate of change,
Slope of
basically
a function.
derivative tells us the direction, right?
Direction in which to move.
Right.
Partial
Yes.
derivative. Yes.
Yes. So it's a simple measure of direction and change, right? So suppose I move in the direction of derivative. How do I move? Like suppose for this function, this is x square, right? The derivative of this x square is 2x, right? How do I move? Like suppose my x is 4, my derivative will be 8, right? 2 into 4. So I'll go here, right? If my x is 4, my derivative is 2x, right? Which is going to be 8. So I'll go here, right? To 8. If my x is 8, my derivative is 2 into 8, which is 16. So I'll go here, right? To 16. I'll move like this, right? Is this the correct direction? Are we moving in the correct direction with respect to the loss function?
No.
Opposite.
No, right? It's opposite. Instead of minimizing it, we are maximizing it. We are moving to higher losses. But if I tell you x square's derivative now, so this is just derivative, okay? This is derivative, is minus 2x. Is this correct now? Is this what I want to do?
Yes, opposite
Yes, we are
direction.
just changing the direction.
Right. So if my x is equal to 2 again, my derivative is minus 4. So instead of like, suppose I was at 2, now I'll go to minus 4, right? Which is going to be here, somewhere here, minus 4. So I'm going to go down, right?
Yes.
When I go to minus 4, it will be minus 8. So I go down even further.
Even
So now
further.
basically I'm moving in the correct direction, right? To minimize the function. So basically the idea is every term in this formula is very understandable. It's very intuitive. Why do I have this negative sign? Because I want to move opposite to the derivative. Why do I have the derivative? Because derivative tells me how much to move, right? It decides the rate of change. But this negative point here decides that I need to go opposite to the direction of the derivative. Because if I go in the direction of the derivative, I'll be maximizing my loss function. So that's why I need to go to the opposite direction of the derivative to minimize the loss function. That's the idea. Is this much clear to everyone? Any question? I think somebody is on unmute. So please mute yourself. Kamlesh, yeah, thank you. Yeah, so any question on this? The idea is clear, like why do we have a derivative and why do we have a negative? I think that's pretty simple, right? Okay.
Yes, sir.
So now let's come to this point. Again, I will take the same figure. So suppose we were here initially. Now we want to move here, right? This is the point where we want to move, and we are moving. Because we have a negative derivative, we are moving here. So we are moving here like this. Now tell me one thing, if I'm moving like this is my movement, right? At every iteration I'm moving like this because my derivative is fixed, right? 2x. So I have this twice movement in every iteration. I come here. Now instead of going here, I go here. Because I have a 2x, I have a big jump. I reach here. Is this correct? Do I want this?
No, we don't want such.
We don't want it, right? Because we wanted to stop here. We don't want to move. And if you want to continue moving, we'll continue moving like this, like this, like this, like this, like this. We don't want that, right? We wanted to minimize here because this is the minimum point. This is the point where you want to end. So how do you decide that my function will come here? This is basically decided by something called as step size. Yeah, learning rate is another term for that. We can think of it like a step size, basically how much you should move. So I'll again come back. This loss function tells you where to move, right? This negative sign tells you go opposite to the derivative because I want to minimize it, right? And this, sorry, this is pretty bad. Let me draw it again. Yeah, this symbol, learning rate or step size, both the terms are correct for this. This tells you how much to move. And why is this important? Because we can, this is called as overshooting the minimum, right? We had a minimum here, but we overshot it and we went here. So we need to make sure that we don't overshoot this minimum. We make sure that this minimum is always reached. So we'll go like this. Maybe we'll go like this. We'll take smaller steps like this, like this, like this, and we reach the minimum and we stop here. That's it, right? So this tells me how much to move, and this prevents missing the minimum. That's what this learning rate does. Okay. Now this learning rate, again, this is a constant. The point is this is a constant. You can like say that for my entire gradient descent, I can take learning rate to be 0.1. That's okay. You can even change it. Like you can say for the first 5 iterations, I can have a bigger learning rate like 1. So I'll take bigger sizes here, bigger steps here, but then I'll make smaller steps like this. Right? So then it will become 0.1 in the last few steps. So the values can vary, or like it will vary. Like it can be the same thing throughout. Also, it can be different values with customization as well. Both the things are possible, but it will be some value, which basically helps me to converge to the minimum. That's the idea, right? Yeah, I think someone has raised their hand again. Yeah, Aviral, yes.
Yeah, sir, as you said that initially we're gonna have bigger steps, then we're gonna have smaller steps. The more nearer we are reaching to minimum, right? So
Right,
how it's
right.
possible? Like because we are fixing the neta, we are fixing, so how it's possible like that?
So see, the idea is it is not possible with this. So this is my formula, right? For gradient descent, this is my formula, right? With this
Yeah.
formula, the eta is fixed. You can see it's a constant. So we can
Yeah.
only use one value throughout. What we do is we take other variations of gradient descent and we use them. That helps. So one variation is called as, so that is I think not in part of this course. You will learn it in the degree level when you go to DL, but I'll just give you a quick intuition on what that is. So instead of having the same formula, we have this. So W1 is equal to W0 minus eta gradient of L, right? Divided by this, some constant. So initially what happens is this constant is very small, so my eta becomes the same, right? But as soon as my algorithm progresses, this constant becomes larger and larger. This constant is not a constant, there's an equation here also. This is basically V1 is equal to V0 plus some epsilon. It's like this. There's also some
Okay.
constant which keeps growing. So once this keeps growing, this will keep shrinking, right? Because I'm keeping
Yeah.
on dividing it by a bigger number.
Yeah.
Right? And that happens. So basically these are called as optimizers. This algorithm is called as ADA-GRAD. These are all variations of gradient descent to make the learning rate better. Okay, we use them.
Okay, sir.
I'll tell you one thing, the plain gradient descent, this is the base of all the optimizers. The base formula will always be the same. But there will be some modifications which will happen on this eta, some modifications which will happen on this derivative to make sure the algorithm becomes even better. We get a faster convergence, right? So to make sure those things happen, we have other variations of gradient descent which are pretty better. Like Adam is one of the ones which is used the most. It's called as Adam. So you can explore that in the internet. It's called as Adam. Right, one more is the ADA-GRAD. So all these variations are there which make sure that we can adjust this learning rate to make sure it has the best possible value, right? We don't fix it, but for our course we'll continue with this one only, where we have a fixed learning rate initially, and that learning rate is what we'll be using throughout. Okay.
Okay, sir. Thank you, sir.
Yeah, any other question?
So Adam makes this eta value as dynamic actually based on this loss and all.
Yeah. It will be dynamic. Like initially it is same, but after iterations it goes smaller and smaller. There is another variation called as ADA delta in which it grows smaller or bigger alternatively. Some step is big, then small, then big, then small. So these are all experiments, right? Some experiment gives us a better relation, some experiment does not give us a better relation. So many of these algorithms have been built up.
So that is one sort of oscillation.
That is not a
Interesting
part of.
oscillations to stop at minimum.
Yeah. So see, if I vary the learning rate, I can have more oscillations. Like suppose in RMS, like this ADA delta, what happens is you have a larger learning rate, then small, then large, then small, then large. So again, it overshot, right? Something bad happened here. So again, it keeps depending. Like for every setup of a network that you take, the optimizer keeps depending. But currently, the industry trend which is going on is on this Adam. this is performing very well. So in all possible forms of data, this has a very complicated formula, so I'll not reveal that right now because that will become a little too much for the session. But the idea is this Adam optimizer and all these other optimizers, they make sure that
Then
this learning rate is robust.
that time and space complexity will suffer because of this.
Yeah, it like space does not. You don't have many variables in it, but time can. Yes, because you do have some more calculations. That is true.
Okay, time
Yeah, yeah.
complexity.
And
That's
actually,
it.
we will talk about time complexity right now because there are some variations, like initial variations of gradient descent, but the formula is same. But there are some calculation variations that we do to make sure that the time complexity goes down. That I'll talk about today itself.
Right.
Yeah, but in optimizers, the formula only changes a bit, where the eta becomes a little different. That we'll not talk about right now. That is not part of our syllabus currently. Okay. Yeah. You learn it in degree level. We also have DL, so in that you will learn it in detail. What different methods are. They're very interesting. You can even explore them about online. Like you can see some visualization on them online and how they work. That will help you to understand how we can actually customize these things. But the main idea is the base formula. This is same. No matter what optimizer you use, the base formula is gradient descent because this is the best technique. Okay, that is pretty simple. Yeah, so I think with that we are done with gradient descent. So any questions on that? Is the idea clear? Like why this formula works? Is that clear now? All the terms, the negative, the eta, and the derivative, everything is fine, right? Yeah. Okay. Great.
Yes, sir.
Yeah. Okay. Okay. So I think that is done. So let's now move on to the next part. Yeah, so let's move on to the next part. The next part is the variations of the gradient descent. I think I was supposed to do it on this slide, but I'll make a new one. I'll just copy this image. Yeah, so I think what we saw right now was a simple gradient descent update, which was basically going like this. So I can even call it like this, right? It was going like this, like this, like this, and it was reaching the minimum. Okay, now if you see a simple thing, this gradient descent algorithm that I'll again write the formula W1 is equal to W0 minus eta times this derivative of the loss at that iteration 0. Now in this formula you can just see one weight, right? But if you have a neural network, there will be thousands of weights, right? Thousands of weights, thousands of biases which will be there in the network. So do you think computing this formula for thousands and millions of weights, actually not even thousands, it will be millions and billions of parameters, to compute these weights for these things, to compute the derivative for all these million parameters, do you think it's an easy thing or it's a very computationally expensive thing?
It's expensive.
Very expensive.
Expensive, right? Because I want to compute a derivative and I want to compute the derivative of million things. So this matrix, the gradient matrix is going to be huge. Massive matrix you'll have, right? And massive matrix on the weights also. So it's going to be very big computationally. So when I do this gradient descent, normal gradient descent, I will actually with all my data, so I'll take all my data, right, to do this gradient descent. It's going to be very expensive and this is going to be very slow. Because it's expensive, it's very slow as well. So this movement which you see is actually very slow. It's like this. Right? It's very slow. So how do I actually make this fast? So to make this fast, we have two variations. These are not different algorithms, like Adam and all were different algorithms. These are gradient descent only, but they have a different variation. The formula is same. The first variation is called as, let's talk about the other one first. The first variation is called as SGD, stochastic gradient descent. So what is stochastic gradient descent? The formula is same, okay? The update rule does not change anywhere. The idea is use 1 point and 1 weight at a time. So basically what I'm trying to do is I have thousands of and millions of points. I will update the weight for 1 point at a time. Like I have many data points, right? In my algorithm, I have multiple data points, which I'll be using in my training data. I'll do the algorithm for once every point, right? So one update every point I'll do it. So basically, for example, if my training data contains of 200 rows, right? So I have 200 data points. I will do 200 updates. I'll do 200 updates because I'll do one update for every point, right? So I'll just do W1, then I'll have W200 and so on. So all updates once for every point. So I'll do as many rows I have in my data will be the number of updates I'll do to the weights. Is that clear to everyone?
And this will be done in one epoch.
Yeah. So in one epoch, you will have 200 weights.
Okay.
200 updates, sorry. Okay. In the original gradient descent, that is also called as batch gradient descent, the original one, we only did one update per epoch.
Per epoch.
Yeah, where we basically took all the data, right? So we had those massive matrices. This becomes massive, this becomes massive. If I just take 1 point every time, the matrix does not become massive, right? It's just a single point. So I just have 1 point here and 1 point here. It's very simple to compute, right? So this one STD is very easy to compute. But do you think there are some variation, like limitation on this, something bad about it? It is
Yes,
easy
sir.
to
A
compute.
number of epochs are more.
Correct. So basically I'll have to run my, just a second. Yeah, so I'll have to run my algorithm for more epochs, right? Because if I have to update once for every epoch, the algorithms will have to be updated for more epochs. Can you tell me one more thing? Do you think that the accuracy of the updates will be impacted by STD? Some problem can come in the accuracy?
Convergence will be erratic, not smooth.
Exactly, right? So basically in STD, my movements are going to be very erratic. It's going to be like this. Why is it erratic? Because to make the model train on all the data, I need to make the model train on all the data, right? And I'm training on 1 point at a time. So I'm taking 1 point and I'm approximating all the data with that just 1 point, right? So my updates are not going to be very smooth. The gradients are not going to be very exact, and my results might be bad. The problem of STD is results might not be great. Okay, but the advantage of STD was that it's very fast. It does a good job in terms of speed compared to normal gradient descent because you are just taking 1 point. There is no matrix and no multiplication and all, simple calculations, right? So what the researchers did was they combined both of them. They took STD's advantage, they took BGD's advantage, and they combined them into something called as MBGD. This is called as mini batch gradient descent. So what happens here is, suppose this is your training data. This has 200 rows. What I'll do is I'll divide this data into some batches, right? So I'll take 50 rows in my first batch, 50 rows in my second batch, 50 rows in my third batch, and 50 rows in my fourth batch, right? And what I'll do is I'll do this formula 4 times. Once for this batch, once for this batch, once for this batch, and once for this batch. So basically one update per batch. That's the idea. Okay, I had 200 data points. I took a batch of 50, so I have 4 batches. So basically, I'll do 4 updates, 1 update per batch. So can you tell me, am I able to solve the problem of both of these using this one?
Yes, sir.
Almost, yes.
So
Almost,
here,
right? Not
epoch
exactly.
size
But
is
almost.
reduced, no, sir?
Yeah, can you repeat once again?
Epoch size is reduced.
See, the idea of epoch size is the updates will become more than this one, but it will become less than this one. So you'll go into some middle ground, right? The middle point of updates. It will be more than BGD, but less than STD. You'll be in a middle point, right? So basically, for BGD, you just had 1 update. For STD, you had 200 updates. For this one, you have 4 updates, right? For this data. Got it? So the epochs will increase compared to BGD, but not that much. It will be a controlled increase. So basically, my convergence, if you see here, this convergence will also be somewhere in the middle. Not as exact as BGD, not as rough as STD, but somewhere in the middle. And the second problem which was there, which was the accuracy problem, here, this accuracy is better. Because basically for every update, you are taking some proportion of the data and approximating it. Here you were earlier just taking 1 point and approximating it. Now you're taking around 50 points, 1/4 of the data, and you're approximating it. So obviously my accuracy is going to be better. Not as good as this, but better. And what about the speed? Again, it's fast as well. Right? Because you have less updates. Here you had 200 updates, here you have 1, but here you have just 4. Right? So speed is also quite good. That's the idea. So what MBGD does is it is a middle ground between STD and BGD, and it takes advantage of both. Its accuracy is very good, not as good as BGD, but very good. And the number of updates that it has to do and the calculations are also quite easier to do as compared to STD and BGD. That's the idea. So is the idea
So
clear?
little compromise is done on both the parameters, isn't it?
Yeah, on weight and bias both. Yes.
Okay.
So everything that is done is on weights and bias. So I'm just saying the example of weights. For bias, you have the same thing, right? So B1 is equal to B0 minus theta times gradient of B0. Same thing. For both of them you are. Okay. Yeah. So is the idea clear? Like what is the difference between the gradient descent, STD and
Yes,
BGD?
sir.
Great. Okay. So if I say batch gradient descent or gradient descent, that means the same, the default one, right? If there is a difference, I'll tell whether it's STD or MBGD, we'll be specifying it. Right? By default, we'll go with the same one, and unless and until specified. If specified, then you go with this or go with this, right? You can see the GI. I think you'll have questions on this. Okay, so I think that is clear. So yeah, any other question on this?
Sir, is BCD also called as vanilla
Yeah, it is also
gradient?
called as vanilla gradient. Vanilla means the plain one, right? So it's also called vanilla.
Okay.
Yes. Right, so even the vanilla gradient descent, that term also we can use for BGT.
Sir, for
Sir, just
BGD,
Yeah.
but you have written one update per after that.
Epoch. Actually, the space is quite less, so that's why I have to clutter it a bit. So it's epoch. Okay, per
Sir,
epoch. So
what is
epoch is
epoch?
iteration. The epoch means iteration. You see the entire data, seeing all the data once. That is an epoch, right? So I'll just mention that. So yeah, so that's also an important term for the thing. So epoch means see all the data once. So basically, I have a lot of data, right? And I have to make the model see all the data once. That seeing all the data once, that is called as an epoch, right? So it's a little different from iteration. One epoch can have multiple iterations. The idea is if you use BGD, one epoch equal to one iteration, because you only do one update, right, in the entire epoch. If you talk about MBGD, mini batch gradient descent, then you have one epoch, but you have more updates, right? So suppose the batch size is B, so you have B updates. For all the batches, you do the update once, right? And that's why you have B iterations as well. B iterations. So every time I'm doing an update, that is called as an iteration. And in SGD, I have one epoch again, right? I have X updates. Suppose I have X data points, I have X updates, right? And that's why I have X iterations. Okay. So seeing the entire data once, that whole cycle, it's a complete cycle. Okay, so you can think of it as a cycle where you see all the data once. That is called as an epoch. Within an epoch, you can have only one iteration. Iteration means the update, right? So if you're using a simple BGD, then you have one iteration and one epoch. That's the same thing. But if you're using some variation like MBGD or SGD, then in one iteration, one epoch, you have multiple updates, right? So you have multiple iterations. That's the idea. Epoch will always be one, which is seeing the entire data, but iterations will depend on what type of algorithm you're using. Okay.
Yes.
Yeah, think of it as a cycle. You see the entire data once. So suppose this is my data. When I see when my model sees all the data once, this whole thing is one epoch. Okay, that's the idea. Okay, yeah. So yeah, any other questions on this?
Sir, I just want to ask one thing.
Yeah.
Regarding the lecture, like today your was first session, right?
Second session. We had a
No, this
session
is
last
the
week.
second session. He
Second
also
session.
did last week.
Okay. So like your session is really amazing. Like I can understand very clearly. So if you continue to take more and more, like that.
Yeah, we'll do a session every week. For all the weeks, we'll do. Okay, and if required, you can message me as well. Like, we'll do whenever required. Okay. So
Okay,
yes.
and you will only cover theory or also practical coding?
No, I'll be covering theory, and the other instructor, I think, Levin sir, you will be covering the practical.
Okay, sir.
Okay.
Thank you very
So
much.
yesterday, I think you had practical class, right? Friday.
Yes, sir.
No, sir.
Yeah. So Friday will
Yes,
be
sir.
practical, then Saturday will be theory. Okay.
How can I reach you? Like,
Can you repeat again?
how
I'm
can
not.
I reach you in case if I want to reach
You
you?
can tag me on Discourse, right? So you can tag me on Discourse. This is my tag. I'll just.
Sayan, here your
Yeah,
name.
no. Tag me like this. You have to tag it like this. My tag is not my name. It is this one. Tag me like this. Okay. Use this and tag me on
Okay, sir.
Discourse.
Thank you, sir.
Okay. Yeah. All right. So yeah. Any other question? Is this clear so far? So this is something you need to be clear about, because we can give you questions on this, okay? Calculating the updates and how many updates will happen in one epoch. So this is something pretty important for the exam point of view as well. Just a second. So yeah. Okay, so any other question on anything on week 2? Like, I'll just share the screen again. I think some glitch happened.
Sir, there was a topic related to preps from.
Which one? Can you type it once in the chat? Like, I'll just check what it was. So we have a little more to cover, so I'll be covering a little more as well. So I was just saying that gradient descent part is done. So we'll now cover the backprop one. Okay, so yeah, so let's cover the next one.
So just one thing, like, what will be the schedule for concept classes?
Schedule for classes will be the Friday and Saturday 8 p.m. Friday will be the practical class for coding, and Saturday will be for theory.
Okay, and any other schedule?
We have TA sessions also. I don't exactly know the
Monday and
timing for
Tuesday.
that.
Monday and Tuesday.
Monday and Tuesday, yeah. So Monday and Tuesday we have TA sessions. TA sessions will be based on your convenience. Like whatever you want to cover, you can tell the TA and they will cover that. Okay. So if you're
Okay,
finding the theory part more difficult, you can ask them to cover the theory. If you're finding the practical part difficult, you can ask them to cover the practical. Or you can do one also. You have 2 TA sessions, right? So one for theory, one for practical. You can do like that as well.
Okay, thank you.
Yes, sir. The same thing was going on in
And who's
TSS.
covering practical, sir? So, what's the name of sir?
Levin
Uh,
sir is doing that.
Puneet,
Levin
sir.
sir, Levin sir.
And
Puneet, sir.
Puneet sir also once he had taken.
Puneet.
You had a class yesterday, right?
Yes, yesterday was
Yeah.
Levin sir's class.
Levin sir, yeah. Levin sir will teach the coding part, right? So he'll use the collab and teach the coding for all the weeks. Yeah, Disha multi-layer perceptron is a neural network only. So basically, we have this thing, right? So this is a multi-layer perceptron, the network. It's called MLP. The neural network is also called MLP because basically at every step you are having this WX plus B, right? Some perceptron or some sigmoid you're having, and you're having multiple layers of this. That's why it is called as multi-layered perceptron. It's simply a neural network, right? Nothing else. Another name.
Okay, sir.
Yeah. So I think we discussed this last week, right? Like how from a single perceptron and single sigmoid neuron, you stack multiple of them and you form a neural network, right? So that's the same thing. Okay. So yeah, any other question? Otherwise, we can come to the next part. Okay.
Is it
Let's come to
possible to
Is it possible to?
this Friday and Saturday sessions are clashing with tools of data science, TDS? Is it possible to
Yes,
make
sir.
it by from 4:30 to 6:30?
I think I don't know if
Means
that can be like
6 to 8. 6 to 8.
6 to 8.
6
Can
to
we do
8.
it like what time is the TDS session?
TDS it starts at 8. 8 to 10.
8 to 10. Okay, on Saturday.
On both days, at least if possible. If at least one day, if it is.
For Saturday, will the afternoon time be fine? Like 12 to 1, 2, is that okay?
Yeah.
Yes,
Sir,
sir.
we have other
Sir, every day.
sessions. Sir, we have other sessions, sir.
Yes, sir. Other sessions are there in the afternoon.
And sir,
also.
I think, I mean, we have to manage somehow because even
Okay, so see,
our
actually,
schedule, there
the
are
thing is
lot of
that
conflicts.
okay, the thing is that there are many subjects in diploma, right? So that's why there is a clash in the timings. But okay, I'll see what we can do. Okay, I'll
Sir,
see.
every day is a clash.
What time? Like any other day you want? Like on Sunday, if we do that, can also be possible.
Yeah, Sunday is also okay.
Okay, Sunday also you have session. Okay.
No, Sunday is
Sunday is fine,
okay.
sir.
Sunday is
Sunday
fine.
morning.
Okay, then we can like if this time okay on Sunday, like the same time right now.
Yeah.
Yes, sir, there are no
sir.
sessions at this time.
Alright, sure. Then we'll do it on Sunday then from next week. Okay.
Better.
Like I'm not
Thank you,
confirming
sir.
it, so just give me one day. Let me talk to the
Yeah.
team and I'll confirm it to you. Right on Discourse, I'll
That
make
would
a
be
post.
great.
Yes.
That would
Yeah,
be
sure.
Thank
You can do that. Okay. So I'll confirm it, and if the timing changes, I'll inform you on Discourse. I'll make a post and I'll update the timings. For my session, Friday you have to talk to Levin sir because I'll tell him. Okay, but for my session, I can take it on Sunday also. That is okay.
Sir, every day there is a clashing because every day TDS session happens from 8 to 10. So that's why 1 hour always conflicting. 9 to 10.
Yeah, got it. So
8 to
Sunday
9.
you don't have, right, for TDS?
Sunday most probably we don't have.
Yeah, sure. Then I'll do it on
Sunday TDS session is from 6
Sunday is
p.m.
there,
So
but it's
there won't be a
4:30 to
Sunday is
6:30.
3
हाँ
to
मतलब
5,
means
right?
timing
6 to 8.
Yeah, then it's okay. Then I'll take my session from
Yeah.
8 to 10, right, on Sunday.
8
Then
to
it's
10.
okay.
Yeah.
Yeah, 8 to
Thank
9,
you.
10, whatever. Yes, that's okay. Fine, I'll do that. I'll update for my session. That's okay. I'll tell the team. I'll just ask them, and if it is possible, then I'll shift it to Sunday. From my side, it's okay. I can do that.
So the calendar needs to be updated so that way,
Yeah. That Levin sir actually manages the calendar, so I'll have to talk to him for it. I'll talk to him and I'll inform you on Discourse like what the update is. Okay.
Sure.
Yeah. Okay, so one small topic is there. Now, this is not a topic, it's something again you're going to use in upcoming week. So I'll just cover this up because I think last week this got skipped by mistake. So this is the softmax function. Now, softmax function is also like the sigmoid function only. So don't memorize the formula. It's a very simple formula. You will be able to learn it once I explain it to you. So if you remember the sigmoid function, what does the sigmoid function give you? Probability, right? So it gives you a probability.
Yes.
So basically, if I say I have two classes, which is spam email and non-spam email, and I basically get the probability of the email being spam from the sigmoid function. For example, the probability is 0.7. What will be my answer? It will be a spam, right? Because that's what my sigmoid is given. And if my probability is 0.3, I'll simply say it is non-spam.
Non-spam.
Now suppose I have another category, partially spam. Can I derive that from sigmoid? Like suppose I see my probability is 0.1. Where do I put it?
So
There is
what's the
no
question?
hard and fast
Non-spam,
rule here,
0.1.
right? We can't actually determine where to put it. Right? We can decide some thresholds like less than 0.2 can be spam. But suppose we have 10 classes like this. We have 10 classes. Then we have to manually set up multiple thresholds, and that's going to be very difficult. Suppose you have 1,000 classes. Then it's very difficult, right? Because probability is 0 to 1. How will you divide this into 1,000 intervals? Very difficult, right? So basically what I want is sigmoid will only give me probability of one thing, which is spam, right? And if it is high, I can say it's a spam, and if it's low, I can say the non-spam straight away from that probability. Now what I want to do is, I think someone raised hand.
Sir, can I please request you to be slow on pace while you
Yeah,
talk?
sure. If I'm going fast, please stop me, okay? I'll go slow. Yeah. So what I was telling is, this sigmoid function, this basically gives you a probability, right, of one class. If that probability is high, I can classify it into that class. If that probability is low, I can classify it into the opposite class. That is pretty simple, right? But in case I have multiple classes, like 100,000 lakhs of classes in my data, can I do this classification using sigmoid? That's my question. What do you think? Difficult, right?
It will be difficult.
Yes, very difficult.
No.
But basically, if I tell you there is a function, okay, I'll again take a new one. There is a function. Suppose you have three classes. Let's assume that for four classes: dog, cat, owl, and mouse. I'm doing this classification, and I tell you there is a function. There is a magic function which gives me probability of dog is 0.3, probability of cat is 0.2, probability of owl is 0.5, and probability of mouse is 0. Is this what I want? Can I straight away then say it's an owl?
No.
I can, right? Like if you see the probability that I'm saying there is a 30% chance it's a dog, 20% chance it's a cat, 0% chance it's a mouse, and 50% chance it's an owl. So I can classify it into an owl, right? Based on my probabilities.
Yes.
I can do that, right? Suppose for another point, this is 0.1. For 0.2, I have this as 0.6, this as 0.2, this is 0.1, 0.1. Can I confidently say it's a dog?
Yes.
I can, right? So basically, if you see this and if you see this, can you give me a statistical name of this? Have you seen something like this in statistics? What is this called?
Probability distribution.
Yeah, probability distribution, or it is also called as probability mass, right? PMF, probability mass function.
Probability mass function, yes.
Right? So basically, what does probability mass function do? Whatever classes you have, it basically gives you a probability of the point belonging to every class. And whatever is the highest, that is your classification. Straightforward. Right? So again, suppose I have this 0.7, 0.1, 0.20. This is my answer. Straight away, right? Can you tell me like what are the properties of probability mass? There were two properties. If you remember from your stats courses, two important properties were there. Can you list
It
them?
will add up to
The
1.
independent.
Yeah, sum is equal to 1, and then
It
all
will
the
be
values
less
are
than-
non-negative, right?
Non-negative.
Because they are probabilities, they can only range from 0 to 1. They can't have negative values. Now let's look at the softmax function and let's see if the softmax function does this for us or not. Right? So let me go to this function. So what is this function doing? This formula. So I'll take a new page, make it a little clear. So what this function is doing? It is doing a simple thing. It is taking e of a1. What are a1, a2, a3? That will come to later. Divided by e of a1 plus e of a2 plus e of a3 plus e of a4. This is the probability of point belonging to class 1. For class 2, I'll simply take e of a2 divided by this entire sum. So do you think it is doing the same thing that I wanted it to do? Let's assume the values
Yes,
are
sir.
this.
Yes.
Will add to
Five.
also.
Yes.
For the first one, I'm doing 3 upon 3 plus 4 plus 5 plus 6. And what is 3 plus 4? 7 and 5 to 18. So this is basically 3 upon 18. For the second one, it is 4 upon 18. For the third one, it is 5 upon 18. For the fourth one, it is 6 upon 18. So all the values are non-negative. And if you add them up, 3 plus 4 is 7 plus 5, 12 and 6, 18. The sum is also 18 upon 18, which is 1. right? So it's doing the job. It's giving me the probability. This is a 1 by 6 probability, right? This is a 2 by 9 probability. This is approximately a 1 by 3 probability, and this is approximately, this comes out 1 by 4 probability, and this is a 1 by 3 probability. I'm getting the probabilities, right? So if you see this, I'm getting a distribution where all the values are non-negative, and the summation of all the values is giving me 1. I'm getting this, right? Whatever I wanted the function to give me, I'm getting it from that function. Correct?
Yes.
Right? This is what the softmax function does. The only difference is, instead of taking these values as these constant, this A1, A2, A3, what are these? These are simply your scores, Wx plus P, Wx plus P, right? Simple scores. So basically in sigmoid also what you used to do, you used to pass it to this thing, right? This was sigmoid. If you remember from week 1, this was sigmoid. You were passing the score here, right? In the same way now you will pass the scores to the softmax function and you'll get the answer.
So softmax is like a combination of many sigmoids.
Kind of. You can think of it as sigmoid for 1 divided by sigmoid of 1 plus 2 plus 3 plus 4. Like this. Right? It's not exactly a sigmoid because you can see this formula is slightly different, but it's kind of approximating a sigmoid. For
So it's a
multiple
generalization of sigmoid, because sigmoid has
Yes.
2 values.
Correct.
Right? Here you have multiple values.
Correct. The idea is sigmoid will give you a probability, right? And from that probability, you can either say high or low. Only two things. You can't say middle, right? So if you want to predict the probability of every class, you can use a combination of these sigmoids into a softmax. That's the idea.
So without this softmax, we will be having like 1 and rest are 0.
Yes, correct. We'll not be able
with,
to get any probabilities. With this softmax, we'll get the exact probabilities for all the classes.
Oh, got it, sir.
Okay. So basically, whatever are the number of classes, this denominator remains the same. This is just the sum. This is always the same. This becomes all the individual values. So first it will be 1, then 2, then 3, then 4 for all the classes, right? So on. And what you will get is this probability distribution is outputted. And using this probability distribution, whatever is the highest probability, that becomes your class. So you can do this classification here. So can I just say sigmoid is the function which you should use for binary
classification?
Yes. And softmax will be for
Multi-class classification?
Correct. Right. So this is for multi-class classification. That's the idea, right? So if your problem is a binary classification problem, my output of the neural network can be a sigmoid. But if the problem is a multi-class classification problem, then it will be a softmax straight away, right? I'll get the probabilities for all the classes and I'll just take the maximum. That's it. Okay, another question. Can I use softmax for binary? Is this possible?
I think yes, we can.
Yes, sir. Yes.
You can, right? Because what will that be? 1 upon 1 plus 2 and 2 upon 1 plus 2. Again the same thing, right? 1 by 3 and 2 by 3. You get the probabilities for both. But you can't use sigmoid for multi-class because that will only give you one probability. It will not give you probabilities for all the classes, right? So that's why it's a convention. Whenever you have a binary problem, you do a sigmoid. Or you can also do a softmax, but you prefer a sigmoid because it's a simple function, right? Softmax is quite computationally expensive. You have many exponents here. In sigmoid, you just have one exponent, right? And whenever you want to do multi-class classification, you do a softmax because you don't have a choice. You can't use sigmoid here, right? The only limitation for softmax is it's expensive to compute. When we move to later weeks where we look at language models like GPT, then you will understand that this problem is quite big. The softmax computation is a big problem. Okay, so we have solutions for it that we'll see later. But this issue is there. And why it's expensive? Because you have many exponents, right? So if I have 100 classes, I'll have 100 exponents in the denominator, right? That's why it's slightly difficult to compute. The rest is fine.
And more the exponents, the time consumption will be again.
Yes. Because suppose you have million classes, so there'll be e million times, right, in the denominator. And e is an expensive operator. E is exponent, right? It's going to be difficult to compute it. For sigmoid, irrespective of anything, I always have one e, right? It just has one exponent. But that's why it only gives for two classes, right? For softmax, we have multiple classes, so we'll take multiple exponents to do that. Okay. Okay, one thing I'll give you for like kind of a home assignment, just explore that why do we need this exponent in softmax? Why not just take the scores like A1 upon A1 plus A2 and so on? Why do we need the exponent? It's something you can explore later on. There's a good research on this as well, why this exponent is actually needed. So you can explore that and maybe in the next session we'll take that up. Okay? Right, so any question on this so far?
Sir, is it like the reason like it can be negative the probability?
Yeah, exactly. When you take the E, it will not be, right? That's the reason. That's one of the reasons. Explore it a little bit more. You'll understand why do we have this E. Others, can you? That is a very good reason actually. Others, any other reason you can think of? Is that the main reason?
It's easy to back propagate like for different
Yes, Exactly. That is the most important reason. When you have exponents, you can take derivative, right? So what is derivative of ex? Ex, right? Same thing. Derivative of ex is ex. You have a well-defined derivative of exponents, right? So you can actually backpropagate. That's the thing. You can do the gradient descent because for any neural network, you have to do gradient descent. Right? That's why I told you everything has to be convex. Loss function, even activation functions have to be convex. That's what I was coming to. Activation functions also need to be convex because you have to make sure there is a derivative defined. If not convex, at least they have to be differentiable. You need to have a derivative. If there is no derivative, how will you compute the gradient, right? That's the idea.
Sir, we can also differentiate other functions, right?
Yeah.
Right.
Multiple. So if you remember last week we discussed about ReLU. We can differentiate ReLU as well, right? In
Then
positive side.
why we need exponential then?
Exponential because the idea is you have to have non-negativity and differentiability, both of them. Okay, if you don't have a non-negativity, then the values become negative here. And in negative, if something becomes more negative, then it's difficult to propagate the network using negative values.
So exponential is the only function that provides both of these things together?
Yes, it is one of there are other functions as well, but as per the current research, the exponent was the one which was used. Okay, there can be more as well. You can discover more, but currently this is what is preferred. Okay.
Sir.
Yeah. So, okay. So any doubt on softmax? So I think now this is the most important one, that sigmoid is used for binary and softmax is used for multiclass. That's the main idea. Okay.
Not a doubt exactly, but how do we decide which activation function should be used in a hidden layer and which should be used in an
That is
outer?
a very good question. So again, for that, there is no hard and fast rule, but there are conventions. Okay, so what are the conventions? The convention is at the output layer, I think this is pretty clear. You can use either sigmoid or you can use a softmax, right? This is pretty clear based on the problem. In the hidden layer, there are many choices. So here you can use ReLU family because as I told you, ReLU has many variations, right? We saw one or two variations last week also. So you can use the ReLU family in the hidden layers. You can again use sigmoid because sigmoid is fine. You can work with probabilities in the hidden layers as well. It also works. Initially there was sigmoid everywhere. There is another function. I think we're not exploring it much here. That is called as tan edge, right? That is another function which is there. We can use this as well, right? So how do you decide what to use? You can experiment with your architecture and see which is giving you the best result. That is the easiest way. The other way is you follow the convention, and the convention is using the ReLU family. Why ReLU family? Because all these functions, they have exponents. This also has exponent. ReLU is what? Simply this function and max of 0 and x. So there is no exponent here. So it's easy to compute. So we'll use this. Same, right? In the ReLU family, now again, that is again slightly difficult to comprehend initially, but you can go and search about it. There's a function called as GELU, Gaussian ReLU. So this is the one which is used the most nowadays in the hidden layer. But you can think of it as ReLU. ReLU family is what we use. So generally what we do is output is sigmoid or softmax based on the problem, and the hidden layer will always be ReLU. That's the main convention that we'll follow. Okay. Again, these are conventions. These are not rules. Like you don't need to make sure this is what you can even try with the others. But based on the research, these are ones which are most effective.
Okay.
Yeah. Okay. So, right. So I think that's
hidden layer can be like a ReLU or like a leaky ReLU for.
That's why it's what about ReLU family, right? You can use any of the ReLU variations. Leaky ReLU. Then there is a called exponential ReLU. But again, that has a problem. You have the exponent, right? So you don't want to use that. And then a GELU. GELU is Gaussian ReLU. It has some probabilistic notations on it. So that is pretty good. Nowadays in all the modern LLMs, that is the GPTs and all, we use GELU. This is most used. Right? But in simple networks and CNN, next week I think you'll see CNNs for images, so that you use ReLU. This is pretty much used. Again, all conventions. You can experiment with others also. There is again no rule on this. But these are what mostly the researchers are using nowadays.
So can you go 2 slides back once?
2 slides back. Okay, this one?
Yes, sir. This you told it will be e power x. So after differentiating also, where was that?
It was here itself where he was explaining
One slide
that
back.
it has a
Even
definitive derivative. Yes.
Yes, sir.
I think here it is.
Yeah, even after differentiating, let's say e power x. So like if we get another function after differentiating, like some other tan h or something, then what's?
So if you have a tan h also has similar form, right? You'll be able to differentiate it. You'll get an e power x and that also. See, I'll tell you something. Whatever functions you use, there are defined derivatives for all of them. So all these functions that you are seeing in the course are basically the functions which are used in the network. So why are those particular functions decided? Because they have a derivative defined. So for softmax, see the formula for the entire softmax, you have a big. I'll just show you. So sorry, my throat is a little bad today. So if you see the softmax function has a derivative defined. This is the derivative. of the softmax. Okay, again, it's a big equation. You don't have to work on this. This is a huge thing. This is the derivative of softmax, which is defined. In the same way, if you want to see tan h, there is a derivative defined for this also. This is a derivative. 1 minus tan h of square. This is a pretty simple one. For sigmoid, you have a very simple derivative. So I'll just show you what the derivative is. So sigmoid
No, sir,
derivative is pretty simple.
if we have here instead of e power x by summation of e power x, tan of h into some function by summation of tan h functions, something like that, then
that's why we don't have, right? Because those won't have derivative. That's the idea. So see, the idea is we are using these specific functions only because they have derivatives and most of them are convex. That's why. Otherwise, you can even use this, right? Sine of x. Why not use sine of x? Sine of x also has derivative. But there are researchers have experimented with all this and they have seen that some functions derivatives are difficult to compute. They are more expensive to compute. So they have decided on those functions where derivatives can be computed and they're easy to compute.
Okay, e power x is like the most easiest thing.
Yeah, because you do e power x and you get e power x, right? Straight away. So there is no computation. The derivative is same, right? So suppose e power x was 0.1, the derivative will also be 0.1, right?
Yes. Okay. Thank you, sir.
Yeah, so that's the idea. For sigmoid, the derivative is also simple. Sigmoid into 1 minus sigmoid. So for example, sigmoid of 1 is 0.73. So the derivative is going to be what? 0.73 into 0.27. This is the derivative of that. Again, very simple, right? And tan h is this. If you have tan h of x, so suppose tan h of x is giving you 1, derivative is what? 1 minus 1 square.
1 square.
This one. Or 0, sorry. 0. Right? So these functions will always have simple derivatives. I'll tell you one thing, that for the exam point of view, remember this one and remember this one. This will be very handy. You can derive it, but if you sit and derive it, you saw the calculations are pretty lengthy, right? To derive these things. So it's better you remember this for the exam. If you have any backprop questions, this will help you. If you remember this. Okay, these are shortcuts.
Is this a into a sigma into 1 minus?
Yeah, so basically if sigma is giving you this value, the derivative is this value into 1 minus this value.
Okay. This is for tan h, right?
This is for sigma.
No, sigma.
So I'll make a slide on this. Just a minute. I'll write it on a slide so that you can see it in the notes. So for sigmoid, this is sigmoid. The derivative is sigmoid into 1 minus sigmoid. Okay? And for tan h, the derivative is 1 minus
tan h whole square.
Tan h square. Okay? Tan h of x square. That's the idea. Okay? So these values, whatever you will get in the activation function, use those values and you can compute derivatives for both of these. Right? And for softmax, you don't need to learn the derivative formula because that's pretty big, which you saw. You need to understand how the function works. That is sufficient. Right? That is sufficient. The idea is it can be differentiated. That we saw. There is a good article on softmax derivative. I'll share that on Discourse. You can go through that. That is pretty good and it explains how the derivative actually works. Okay, so clear? Any question on this?
So on the previous page, there is a question. Can you solve it?
Yeah. This is a full ANN propagation. This is actually a homework question, but I will solve a similar question today. It is this one. This solved in the lecture. I'll explain you this because it's all written, right? It will be done fast. Then you can try this question in the as your homework question. You can practice this out. And what I'll do is I will also tell the TA to take this question up in the TA session so that they can solve it and you can understand how this entire process works.
Okay.
Yeah. This is basically the same question with some larger values, but values are zeros and ones, so it will be easy to calculate. You can expect questions like this in the exams as well, like similar things like this, so that you can basically to understand if you're able to go through a neural network concepts properly or not. Okay, so this I'll take this question and end today's session. But so far, are the concepts clear? Any question on softmax and derivative? If there are any questions, you can ask. Otherwise, we can move to the last part of today's session.
Sir, could you please explain the last part that you derive the formula for softmax?
Formula for softmax. This one. This one.
So after that, there was a quiz. Yes, sir.
Yeah. So basically, this is basically this one. You want to explain this one, this formula?
Yes, sir.
Yeah. This is what it's showing us. Simply, you understood, right? The softmax function will give me a probability distribution, right, for all the classes. How will it give me the distribution? It will just take the scores for all the classes from the network, which is this wx plus b, right? This is a score, and it's straight away going to pass the score into the exponent. and it's going to divide it. So basically, E of W1 x1 plus B1 divided by E of W1 x1 plus B1 plus E of W2 x2 plus B2. So basically all the scores, it's taking the scores for all the classes and it's just dividing them to get a ratio of all the classes, right? So I took an example here that if the scores were 3, 4, 5, 6, the first probability will be 3 upon sum of 3 plus 4 plus 5 plus 6, which is 3 by 18. Similarly, the second probability will be what? 4 by 18, right? 4 upon the sum. Third will be 5 by 18 and the last one will be 6 by 18. So basically you are just taking the individual score and dividing it by the sum of all the scores to get a distribution, right?
Yes, sir.
Yeah, so it's simple, right? I'll take an example, numerical example also, so that it will be more clear with that.
Okay, sir. Why you have written 1 by 1 plus e power minus wx plus v?
This is sigmoid. I was explaining something about sigmoid here. This is not softmax. This is sigmoid. I'll delete it if you want.
Okay, sir.
Yeah, I was discussing something about sigmoid here, so I just wrote the formula for that. Okay, this is sigmoid. Softmax is this. This is the softmax. This one. Okay.
Sir, will you please explain back propagation?
Yeah, I'm coming to that. See, back propagation is pretty simple. It is just gradient descent. That is back propagation. You're updating the weights and biases, right? So suppose you have this network. So let's go here. So suppose you have this simple network. So this is input. This is the output, right? Let's ignore the bias for now. Let's just have the weight. W1, W2, and this is y hat. Right? Suppose this is a sigmoid. Okay. So what you do in back propagation is you will just take the simple thing. You will just do gradient descent on this, and you will do gradient descent on this, and update it. That's all. That is back propagation. Forward propagation is passing this wx plus b to the sigmoid and getting this probability. Back propagation is just getting the gradient descent and updating the weight. That's all, right? So whatever we talked about in gradient descent, that this formula, that is w1 is equal to w0 minus eta times gradient of this loss function at 0. That whole thing to update these weights, that is what is called back propagation. Okay, because you're going back, right? From this point, you're going to this point. Okay. This is the main idea. Did you get it?
Yes. Yes.
Yeah. So backprop is simple. Just update the weight. So whenever there is a question on backprop, you just have to update the weight. That is the question. Right? Using the some eta will be given to you. Using that, you have to update the weight. So what I'll do is I will share one backprop question with you on Discourse. Try that yourself to update using this gradient descent. If you are able to do it, well and good. If not, we'll take it up in the TA session or I'll solve it up in the next session for you. Right? But the idea is same. Just use gradient descent, compute the derivative, and you update it. So let's take one simple example. So
Sir, can you take one practice question in a
yeah, I'll take that only. I'll take that. Yes. So let's take one practice question. So just give me a minute. I'll just find the question, which is quite easy to calculate, so we can see it quickly. Okay, so just give me 1 minute. Yeah, okay. So again, we'll take a simple network. Okay, we have x1 and the value of x1 is 1. We have x2, its value is 2. We have w1 which is equal to 1 and w2 which is equal to 0. And we have a sigmoid, right? Okay, let's first basically do the forward prop. So let's first do the forward pass. Can you tell me how the forward pass will happen? I need to basically compute this y hat, right? Can you tell me how to get this y hat?
W1 x1
plus
w2
plus
so first basically
sigmoid of that.
This, right? We have to do wx plus b. Let's assume b is 0, right? For now, let's assume b is 0, so the calculations will be easier. Okay, so basically form the x first, which is 1 and 2. Form the w, right, which is 1 and
1 0.
Okay, I need to now multiply them. So can you tell me how to multiply this? Is this correct or do I need to do some transpose or something? Can I multiply these two?
Yes, sir. Yes, sir.
Because I have
Yes, yes.
2 cross 1
Cross 1 and 1 cross
and 1
2.
cross
1
2.
cross
So
2.
right, I can
1
multiply
cross.
this. Simple.
Yes.
So let's multiply this. So this is 1, this is 0,
1020.
2, 0. Right? We have this. Simple. Now one thing simply that you can do is whenever you have to now this wx plus b is computed, I have to now pass this to a sigmoid, right? To get
Yes.
my y hat. Can I pass this matrix to a sigmoid?
Yes, sir. Each element will be sigmoid of it.
Sir, I think we had that wrong.
No, actually we
Because
can't, right?
double,
Because
double
if you see,
transposits.
I have only one sigmoid, right? One neuron. So I can't pass everything into multiple sigmoids, right? I need to do it once. So basically I need to get a score, like for example 5, and I need to pass this to sigmoid. That's what I need to do. For ReLU and all I can do that, but for sigmoid I need a single score. So how do I do it? How do I convert this into a single score?
Take the determinant.
Determinant by doing.
No, determinant we won't take because we're not going into that. We'll have to multiply the actual weights and get a single score. Can you tell me any way to get a single score from these two matrices?
That length.
Can you flatten?
Can we do some
Dot product.
transpose and will that
We have to do transpose.
Yeah,
W
so suppose I take the transposes, that is 1 and 2, and here I take 1 and 0. Will this give me a 1 cross 1?
Yes, yes.
This will, right? So basically this you remember, whenever you have matrices in sigmoid, you need to make sure that you get a single number. So multiply them to get a 1 cross 1. Okay, that if you remember it like this, then you'll always solve it correctly. So always multiply in the way to get 1 cross 1. Otherwise, in the formula, there are many transposes in the formula also. You don't need to remember that. You just need to remember that I need to get a 1 cross 1. So that's all, right? So if you remember that, I think easily you can rearrange the matrices and you can get that, right? So now let's multiply
Yes.
them. And this is 1 and this is 0, right? So I just have a simple value, which is 1. Okay. So now what I'll do is I will do sigmoid of 1. So can someone calculate? I know the value, I can write it. I wrote it a few minutes back, but can someone calculate it and give me what is the value of sigmoid of 1? That will help you to practice for the exam as well. Use your calculator and just calculate sigmoid of 1. So basically this is what I want. 1 upon
0.37 sorry, 0.731.
Yeah, so 0.73, right? So 0.73. So what is this 0.73? Can someone tell me what this 0.73 is? Is this y hat?
The probability.
Yes, so it is y hat, right?
Y hat.
This is y hat. So basically in the exam, how will we give you the questions? We'll give you some weights, biases, okay, and we'll give you some data points and we'll tell you calculate y hat. So I think now it's clear, right, how we'll calculate y hat?
Yeah.
Yes.
Right, so what you'll do is simple, wx plus b. If bias is there, you can just add the bias. Suppose bias was 1, you'll just add the bias and it will become 2, right? 1 plus 1. Simple. So bias is direct, it's just a constant. So you will simply do wx plus b and then you will pass it through sigmoid or ReLU and whatever. Whatever the function is, you'll pass. So suppose the function was ReLU, then what will be the answer? Straight away 1, right? Because ReLU will take the same value, right? So I can change the function also, right? So you simply get the value and that value is your probability, this y hat. One thing you need to remember is whenever you have a sigmoid or ReLU, you need to make sure that you get a 1 cross 1 output in the end. And this has to be 1 cross 1. So multiply the matrices in a way that you get a 1 cross 1. Okay. In the formula, there is a transpose here. Some formulas have transpose here. So that becomes slightly confusing to remember. So ignore any transposes. Just remember this formula. And when you're multiplying, just rearrange the matrices so that you get a 1 cross 1. Right. That is something I think we can do. Right.
Sir, how are you doing wx plus b? Just like how are you calculating?
No, suppose b was 1. Suppose that b is just a constant, okay? Suppose b was 1.
Yeah.
So wx is 1, right? So I'll just do 1 plus 1, which is 2. And then I'll do sigmoid of 2.
Okay, you calculated wx already here.
Yeah. You calculate wx first. If there is a b, add it up. If there is no b, don't add it. Simple. So basically, this is what? This is 0, right? I'm adding 0 here. Same thing.
Got it, sir.
Yeah. So let me write it here again. So add bias if there.
So it's sigma wx plus b, like you have written.
Yes. So it is sigmoid wx plus b, right? If b is there, add it. If b is not there, you can skip it. Somebody raised hand, I think. No, okay.
Sir, every time is it possible to get to 1 cross 1?
Yeah, it will be. It will always be possible. Okay.
If it is of higher dimension.
No. If there is a higher dimension, then we'll have more layers to make it into 1 cross 1. So at every layer, we'll reduce the dimension. Okay. And in the end, see, the idea is in the output, when you have the sigmoid in the output, you will always get a 1 cross 1. That is for sure. Okay. If it is a softmax, then you need not get a 1 cross 1. Right? For softmax, you will do a ratio of probability. So you can get like this also. 4 scores. Right? And you can do a E of this 1 upon E of 1 plus E of 2 plus E of 3. We'll take an example with that also, but the idea is whenever you have a sigmoid and sitting in the output, you'll always have a 1 cross 1. Because sigmoid only can work on one value, right? I cannot take multiple values to get the sigmoid. I'll only have one value and I'll take the entire thing with that one value. That we know, right?
So the y hat is predicted
Probability.
value.
Yes. Probability.
And
This is the probability.
y is actual, and we need to come.
Y is actual. That will be given to you. So whatever is the y, that we will give you, because obviously that's a label, right? So you cannot predict that. Whatever is the y hat, that you will have to calculate. I think that you can do.
Okay,
Yeah.
y hat equals to sigmoid wx plus b.
Yes. So basically, let me just maybe write some information here that will make it more clear. So we will give you. So given will be x, right? This will be given to you. W will be given. The initial weights will be given. Bias will be given. This can be something or it can be 0 also. And you will get y. This is the true label, right? So true label. And true label will be either 1 or 0 or something like that. What you need to find? So you have to find y hat, which is basically what? Sigmoid of wx plus p. Got it?
You can also find the loss also.
Yeah, that I'm coming to. So the first thing will be y hat. Okay.
Yes.
Now once you have found this y hat, so this is done. Now I'll tell you the next question. So I'll give you a sub part of the next question. That will be calculate the loss. So next question is calculate loss using y hat. So can you tell me how to calculate this loss? Loss will be cross entropy. So this is CE loss. How to calculate this? Y hat was 0.73.
Y into
yeah,
ln
so
of y hat.
Yes, correct. And let's assume y is equal to 1. So it's going to be 1 into ln of 0.73. And just take the negative of this to make sure the sign is positive. Right? Yes. So can someone find this value for me? What is the ln of this?
0.31.
0.39. So this is going to be minus of minus 0.39, which is 0.39. Right? You can ignore all this. You can just assume that whatever value you get, you just take the value. Ignore the sign. Okay? It's always going to be positive. So always positive.
So it's 3-1, not
0.31.
3-1. Okay. Right? This is the loss. So I think this is clear also how to calculate the loss. The idea is once you calculate the y hat, you can simply just do this minus ln y hat and you can get the loss straight away, right? Just use the calculator, calculate the ln value, and that gives you the loss function. Clear, right? Any question on this?
No,
Pretty
sir.
simple, I think this is. Yeah, okay. All right. So now let's do the back prop. So I think forward prop is clear to everyone, right? No questions on this.
Yes, sir.
Okay. Now let's go to the back prop. So for back prop, I'll just...
Sir, before you move on, so whenever there will be question around forward propagation, so always we are asking over the loss, this ultimate value that we just computed, right?
Yes. So we'll ask two things. Like it can be one question that you calculate the loss. You just reach out here. Otherwise, we can give you two questions. Calculate the probability, which is this, and then calculate the loss, which is this. So ultimately, you will reach here only, right? Same thing.
Okay.
So either if you want to give, we can just give one question of higher marks where you just calculate the loss. Otherwise, we can give two questions of lower marks where you calculate that first and then this first. Right? Both things can be possible. But the method is same, right? You in the end you have to end up here only to do something.
Understood.
Okay? Yeah. So this is done. Now let's come to back prop. So for back prop, I'll draw the network again. So this is the network. And here we had this loss, right? Okay, now for back prop, you need to know that you need to basically update this W1 and you need to update this W2. These weights have to be updated, and how will they be updated? The W is equal to W1 is equal to, like on iteration 1, I can call it WT, will be equal to WT minus 1 plus minus eta times this gradient of loss function at that iteration. That's what I'll be using, simple gradient descent, right? Now to use gradient descent, what do I need to do first? Can you tell me what do I need to do first? This, right?
Gradient of loss at the output.
Yes, I need to compute the derivative of this loss, right? Now if you see this loss function which is there, this is the cross entropy loss, right?
Yes.
And how has this loss come? Like what has been used to get this loss? Can I say the sigmoid function was used to get this loss?
Yes, sir.
Because sigmoid function gave me a probability, right? And that probability gave me this loss. So simply I can say this loss depends on this sigmoid function, right?
Yes.
Correct, right? Because using the sigmoid function only I have reached this loss function, right?
Yes.
Yes, sir.
So basically what I need to do is I need to first compute the derivative of this loss function with respect to the sigmoid function. Okay. Now let me tell you one more thing. When you do backprop, there is a lot of calculations and confusions that can come up. So what I'll do is I'll try to simplify this and give you the quick end results, which will help you to directly solve it in the exam. Okay. If you want to see derivations and all, we can discuss that later, but I'll try to make it simple for you so that you can solve it in the exam pretty easily. Okay. Now let's come back here. So you basically have to compute the gradient of this sigmoid function with respect to loss. For this, again, computations are pretty lengthy. You don't need to remember them. You can simply remember it like this: derivative of loss with respect to sigmoid is simply the derivative of sigmoid. Okay, how this has come, we'll not discuss right now because that's going to take some time in the derivation. Remember it, derivative of loss with respect to sigmoid is always a derivative of the sigmoid. And what is derivative of the sigmoid? Right?
Sigmoid times 1 minus
Sigmoid into 1 minus sigmoid.
Right? So basically my first derivative, which is gradient of this loss with respect to sigmoid, this is simply 0.73 into 0.27. Correct?
Yes,
Correct,
sir.
right? Yeah, so I've got this derivative. So basically I have back propagated from here to here. This I have done. I have got the derivative of the loss with respect to the sigmoid. This is done. Is this done? Is my derivative done, or is there something else? I need to basically compute what? My end goal is I need to compute the derivative of the loss with respect to the weights, right? Because the weights are the parameters. The sigmoid is not the main parameter. So have I done this, or do I need to do something else?
Now we need to find the derivative with respect to each weight.
Yeah, so basically the weight matrix, right? The weights will be in a matrix, so I can just find the derivative of the loss with respect to the matrix.
The weight matrix.
Correct?
Yes.
Yeah, so basically what I want to say is, first I have done this, right? So loss is what? Loss is sigmoid of Wx plus P. This whole thing is giving me the loss. So I need to compute the gradient of this loss with respect to this W. So for that, what I do is first I do gradient of this loss with respect to sigmoid, which is this outer thing, and then I'll do gradient of this loss with respect to W, which is the inner thing, right? Doing this whole thing gives me the actual derivative. If you remember mathematics, this is also called as chain rule.
Yes, sir.
Right?
Yes.
So suppose I
Yes.
have derivative of sine of e of x. First I'll do derivative of e of x and then I'll go to the sine, right?
Yes.
Like that. No, sorry. First I'll do the derivative of
First
sine of e of x and then I'll go
Sine
to
of
e
E
of x.
of x and then E.
Right? So 2 times I'll do.
So,
In the same
sir,
way,
it's
first I have the sigmoid. Yeah.
derivative of loss with respect to sigmoid into derivative of sigmoid with respect to weight, right?
Yeah, sorry. Yes, sigmoid. Chain rule, right? Yeah. Thank you. That was a typo. This was sigmoid. Okay, so basically what I'm doing is first I'm doing derivative of loss with respect to sigmoid, and then the derivative which I've computed here, this will go with respect to the weights. So first the outer, then the inner. So I'll basically go from out to in. Okay, and you can remember it with the chain rule. So I think this function gives you a good idea. First you'll compute it with respect to sine of x. So you will first do this like this, right? Sine of e of x into derivative of e of x. Right? This is how you do this. And you multiply these two. In the same way, first compute the derivative with respect to the sigmoid, and then you compute the derivative of the sigmoid thing or this activation with respect to the weights. That's the idea. So any question on this? Clear so
So
far?
if we have multiple hidden layers, then like how it's gonna
Yeah. If you have multiple hidden layers, then you have to do multiple derivatives. So I'll tell you that in a minute. So first let's solve this and I'll give you the example for that. Okay.
It's like this only, like via chain rule.
Can you repeat again?
It's like this chain rule only, like.
Yeah. Chain rule. So basically it's like this. So it's like this.
But the
So
sequence is
derivative of loss
confusing.
with sigmoid, then derivative of sigmoid with W3, let's assume 3 weights are there, then derivative of W3 with W2, right? Then derivative of W2 with W1, like this. Multiple chains. It'll keep growing. So no matter how many hidden layers you have, this is hidden layer 3, this is hidden layer 2, this is hidden layer 1. Right? For each layer it will go one by one.
Right.
This is the output.
Okay, last time sir has taught them, sir has given like A for activation function, W like this they have given. So it was confusing, like which one to include first, like
In
sequence
the
or
lecture slides.
yeah.
So actually in the live sessions, sir used actual notations, whatever the notations are used. So it became very confusing.
Which live session? Levin's session?
I don't know exactly, to be honest, but like AI
It
use
was
Z.
Pulkit's session that day.
Pulkit sir.
Pulkit sir, yeah.
Pulkit, it was Pulkit's session that day.
Is it a TA session? I think Pulkit is TA, right?
Yes, sir.
Yeah, so I think he might have used different notations. The idea is you can ignore the notations. These will all be clearly specified in the question. First, you compute the derivative with respect to the output sigmoid, right? Then you keep chaining it with respect to the weights. That's the idea. Okay, so what we'll do is we'll first solve this question, which we were doing, and then we will solve something like this. Not today's session because we'll exceed time. This we'll solve in the next question. Then you'll have multiple weights, right? So we'll see how the loss propagates through all these weights. Okay, that will be easy to see. And don't worry about this. We'll not be asking you very confusing questions on this. It will be pretty straightforward. It will be clearly mentioned what you have, what has to be done, right? So you'll
Yeah,
not.
but the concept must be clear. So like.
Yeah. Concept is then. I think the concept is mainly this. This is the concept that you have to have a chain, right? You are doing a chain rule here, where you are basically going from the outer layer to the inner layer, right? That's what you
Yeah.
need to do. Okay. And don't worry, I'll talk to the TA and I will tell the TA to take up this problem in the next TA session, because today I think we don't have time. So in the next TA session, we'll take this up so that you can understand how the entire thing is working with multiple layers. Okay, this is a big network. So you can see multiple points and multiple layers are there. Quite a big network. So you will be able to do the same things there. Right? Forward prop is pretty simple. You just need to do Wx plus B and get the sigmoid and get the loss. Right? In the back prop, you need to compute a chain of derivatives. That's going to be slightly tricky. Okay.
Sir, in forward propagation, we use a activation function, right? Like
Yes. We use.
Like here we using sigmoid function.
Yeah,
And
so
then
basically in this question, if you see, you'll have a sigmoid here, then another sigmoid here, another sigmoid here. So you'll have activation function at every layer, right?
okay, uh, got it. So and in backward, we are using like this. You have given this gradient descent something formula, right?
Yeah. In backprop, we use the gradient descent formula to update the weights, and to get that gradient, the derivative, we use the chain rule. Okay.
Okay, so why are calculating gradient descent like in backward for propagation?
No, we are updating the weight, right? In backward propagation, we are changing the weights to minimize the loss, right? We are trying to see this was the loss, we had these weights, now we want to come to this
Got it.
weight, right, which will minimize the loss. So how do you update the weight? Using gradient descent, right? That's why we are
Yeah.
calculating the derivative. Okay.
And those derivative part will be like chain rule. We have to
Chain
apply.
rule, yes, chain rule. Depending on how long the network is. If it's a short network, you just have a simple derivative with respect to the output, right? Which we did right now. And if you have a long network, then you have to do a chain, which is like this. First with the output, then with the first layer weight, then second layer weight, and so on. Right? That will be longer.
Okay, sir. Thank you, sir.
Okay. Yeah, and this will be specified in the question. So don't worry about it. All the notations will be clearly given in the question, so you don't have to get confused. It will be very simple.
Sure,
okay?
sir.
Yeah. So basically now that we have computed a loss function, right? We will now so this loss we computed, loss with respect to sigmoid. This we had computed. So once we compute the loss with respect to the weight, so after the sigmoid, where was the slide? I think it's got a little confusing. Yeah, this one only. So first, basically, let me insert another one. So first, what we did was we computed this loss derivative with respect to sigmoid, and that we basically got as 0.73 into 0.27, right? This was what we got. Now what you do is you
Sir,
compute
is that the always will that always be the case that that derivative of loss with respect to sigmoid is
It'll
always
always be the derivative of sigmoid only. Yes, always.
okay.
Okay, that's why I told you it's a shortcut trick. I'm not going to the derivation, but it's a shortcut trick. You will get this only. Always.
But for other activation function, we will have
For
to compute,
softmax,
right?
you have to do derivative of softmax, but I think we will not be giving you that, most probably. That is pretty lengthy to calculate. Okay. In case we are giving you that, then I will take an example of that in the next session. For softmax. Forward prop with softmax is pretty simple, that you can expect to get. But backward prop, we will see. If it's complicated, then we'll give you the derivative only for softmax. Then you can calculate for the other derivatives after that. Okay. Because softmax derivative is actually a matrix. It's called a Hessian matrix. It's a big matrix which comes up. So computing the derivative there will be slightly more calculative. So we'll check on that. Whether most probably will not give. So don't worry on that. That we won't give. Okay. Then if we give, we will give you the calculation steps and the formula. You can use the formula and get it from there. That will be easy to do. Okay. This sigmoid thing you need to remember that this is sigmoid into 1 minus sigmoid. This has to be remembered. Okay. Yeah, okay, so let me just wind this up then, and then we can have a discussion on the other things as well. So once you've computed this, then you can basically compute the derivative of the sigmoid with respect to the weights, right? And how do you compute this? You want to compute the derivative of this thing with respect to weights. What is the derivative? Can someone tell me?
X.
X, right? Straight away the data point. So suppose my data point was 5. The derivative is straight away going to be what? 0.73 into 0.27 into 5. Right? Straight away. Because the derivative of this thing, wx plus v with respect to w is just x, right? B is a constant and w goes out. You just get the point, right? Can someone just tell me what is the calculation for this? What is the value of this?
0.985.
Okay, let's call it 0.9. Okay, so it's 0.9. Fine. So basically, now what I've done is I've got the derivative of this loss with respect to w, right? I've got this. I first did this, then I did this, and then I multiplied them, and I got the final derivative. So this is my final derivative, right? Correct?
Yes.
Now what I can do is w1. So the other weight also you can do the same thing. For w1, I've got this derivative. Now what I'll do is I will now do the backprop, which is basically the update. So I'll do the
Sir,
update.
what is 5 there in the last slide? Is that
5 is the
x
x value.
value?
I'll just assume the x value is 5.
Okay, hypothetical value. Okay.
Yeah, so let x is equal to 5. Okay. So now let's assume that w1 was, suppose it was 1 initially. This was the initial value. So basically w1 new. So w1 new will be w1 old minus eta times gradient of loss with respect to w1 old. Right?
Yes.
Now w1 old we have, this is 1, this we have, right? The old value. We have the eta, so let's assume eta is equal to 1 also. This also we have, this will be given. Okay, eta value will always be given in the question. Into the gradient. What is the gradient?
0.9.
0.9.
This is 0.9. So what is the final value of w1 new? This is 0.9, which is 0.1. Right? And this basically is your backdrop. You have updated the weight. Got it?
Yes, sir.
Yeah. So basically I'll repeat again what we did from the beginning so that you have the steps. Just follow these steps and you'll be able to calculate. So first what you did was the forward prop. So FP, where you did the WX, right? Then you added the bias if it was there. Then you pass this through a sigmoid. And you get this y hat. Then what you did was you did the loss, right? Which is basically just the minus ln y hat, which is the cross entropy. It can be mean square error also, so that depends on the question. Right? But mostly it will be cross entropy for our case.
So y times minus ln y hat.
This is cross entropy, right?
Oh.
Yeah, and the class is 1, right? So it's basically minus 1 into ln y hat, which is just ln y hat, right?
Okay.
Yeah.
So why ln? So in entropy, y is there na before ln?
Y is a minus before ln?
Yeah, he's saying the formula has y also. Y multiplied by ln.
Yeah, but if you remember, I told you, right? This y is going to be 0 for all the other classes. That will 0 out. And for the current class, it's going to be 1, right? So that becomes simply an ln y hat, right? Straight away.
Okay. Yes.
Yeah. This is simplified. So basically, the formula is what? This is the formula. I is equal to 1 to c minus of y into ln y hat. But for all the other classes, this becomes 0. So this term goes, and for the current class, this y is 1, right? So I can simplify this as minus ln y hat.
Got it.
Yes. Yes, sir.
Okay. Yeah. Okay, then I'll do. Okay, so I wrote bad by mistake. This is back. Right. So then you do the back prop, right? For back prop, what do? You do a gradient descent, right? Which is basically WT is equal to WT minus 1, which is the previous weight, minus eta times gradient of loss with respect to WT. To get this gradient of loss with respect to W, you have to do the chain rule, right? Which is basically gradient of loss with respect to sigmoid, and then gradient of the sigmoid with respect to the weight. And this we have computed, right? This is straightforward, which was just the value which we had seen earlier. It's pretty straightforward. And to get the gradient of loss with respect to sigmoid, I told you a shortcut, and that shortcut was simply that this is derivative.
Sigmoid.
Which is sigmoid into
1 minus sigmoid.
Right, and this will be direct. This is direct. You can solve this directly, right? So once you have computed the weight, the derivative, then you use this derivative here, and you update the value, and you get new, W new, and this is where you can stop. Okay, and this is given. The eta value is given.
Sir, we don't have to calculate this chain rule.
You have to, right? You have to. We did it, right? First, we did the derivative of the sigmoid here, and then we calculate the derivative of sigmoid with respect to the point, right? That also we got. So we have to calculate.
You said that there is a direct formula, this sigmoid 1 minus sigmoid.
Yeah, this is the formula. Yeah. This you don't have to calculate. This is direct, right? Then you have to calculate for this step, which is this x, right? This you have to calculate. For this is direct formula. Whatever value you're getting, this to sigmoid into 1 minus sigmoid. That's straightforward.
Okay, sigmoid by W I have to calculate.
Yeah, this you have to calculate. The loss by sigmoid, that you don't need to calculate because that's
Okay.
straightforward, right? The derivative of sigmoid. How it is, that we did not discuss, but there's some mathematical derivation. But you can just remember that as a shortcut, that the loss with respect to sigmoid is straight away sigmoid into 1 minus sigmoid. Straightforward. Okay?
Okay.
Yeah. If the loss is if the function
Sir,
is
one doubt.
it will be different.
Hello.
Yeah.
So the derivative of so the loss is log of y, right? Log of sigmoid.
Yes.
So the derivative should be 1 by sigmoid, right?
Which one?
Okay, so the derivative of loss with respect to sigmoid should be 1 by sigmoid, right?
Loss. This is not log.
No, it's loss. It's not log. It is loss is this, right? Minus ln y hat by sigmoid.
So y hat is sigmoid actually, sigmoid of z,
Yeah.
correct?
So this is minus ln, correct. That is right. This is sigmoid of wx plus b divided by this sigmoid. Right. So how it is 1 by sigmoid?
So the derivative of log is 1 by log x is 1 by x, right? So so the
Yes.
derivative of log of
But
sigmoid
this is not
should
log
be
x.
1.
This is you can think of it as a division rule. Derivative of a by b. You have a function here as well, right? And you have a function here as well.
Okay.
Think of it as derivative of x by y. So that is what? It is a quotient. You remember the quotient rule, right? The quotient rule of
Yes,
derivative.
yes.
Yeah, this is the quotient rule actually. The quotient rule works here. And that from there we have reached this formula. This one. Okay. So actually, see, this derivation is slightly complicated. So if you want, maybe we can go into it. But right now, just for the calculation perspective, you can just use it as a quick trick to solve it. Right, which is derivative of loss with respect to sigmoid is just sigmoid. Because this is the answer. The answer is this only. How do you approach it? There is some matrix calculations in that, and you have to use that whole chain quotient rule, right? And then when you use the quotient rule, you can approach that. That will be straightforward, but it's slightly complicated to understand how this works. But I think the logic is clear. The trick is clear, right? The derivative of loss with respect to sigmoid is always going to be sigmoid into 1 minus sigmoid. Straightforward.
So
Okay.
we are done with lecture today.
Yeah, 2 more minutes. One more thing I need you to tell. Even for softmax, actually, there is another trick that you can use for softmax. So maybe I'll just tell that as well. So for softmax, if you want to compute the derivative of loss with respect to softmax, is actually a very big thing, which is this whole matrix-based derivative comes in there. But you don't have to do that in the exam. For the exam point of view, you can remember this is, I think just a second. This is y hat minus y. Did you get it? What this means? So if I have a softmax in the output, right, I'll have some y hat, right, with some, suppose 0.7 is y hat and suppose y is equal to 1. So my derivative of loss with respect to softmax is basically 0.7 minus 1, which is minus 0.3. Okay, this you can remember for softmax. So if you get softmax function in the exam as your output function, whatever y hat you get, the loss with respect to that softmax is going to be y hat minus y. This you can remember for the exam. Okay.
So y hat will be given or like?
Y hat you will compute, right, with forward prop. You will compute y hat and then using that y hat, y will be given. This will be given. Y hat you have to compute, right? You have to do the wx plus b and pass it to softmax and get the y hat, right?
Oh,
Y will be given to you. Okay, and then using that y hat, you can compute this derivative, which is y hat minus y.
Got it.
Okay. Yeah, so I'll tell the TA to take one more example like this one. This, if you solve this question, right, I think this will be very clear. I think the basic idea must be clear right now only, but this is a slightly lengthier question. This has softmax in it, so if you solve this, this will be much more clear how to go about this. And if you want, what I can do is I can solve it in the next TA session, in the next instructor session as well. The whole thing, right? If you have a doubt, try it yourself once, or tell the TA to solve it for you as well. That is okay. But otherwise, I will solve it for you in the next session. Because today we are out of time. I think it's quite long today, so we can take this up again. But the idea is simple. You have to follow these steps. Okay. So this is what I told you. First, do the forward propagation, which is wx plus b. Pass it through sigmoid. This can be softmax also. Obviously, this can be any activation function. Get y hat. Using y hat, use the cross entropy loss and get the loss. Once you've got the loss, update the weights using gradient descent, where you basically compute this gradient using the chain rule. Right? If you have sigmoid, then it becomes sigmoid into 1 minus sigmoid to solve it easily. And if you have a softmax, it is just y hat minus y. Right? So these are tricks. These are simple tricks which you can use to make it quite easy for the exam. Okay? That's the simple thing. So I hope the trick is fine, right? You have understood how to go about this for the calculations.
Yes, sir.
Yes, sir. Thank you.
Yeah. Okay. So any other question? I think this was the full pass. This was the backdrop part as well. Don't worry about the backdrop part. Okay. So everything will be specified clearly in the question. It won't be very difficult to do in the exam. It's pretty simple.
Thank you very much, sir, for this amazing lecture, sir.
Thank you. Thank you so much. Yeah. Others? Any other question? Otherwise, we can wrap up. Okay. I think it's clear then. Great then.
Yes,
So
sir.
we'll meet again next week. Next week we have week 3. So we'll cover week 3. And if this is required, I'll solve the softmax question also if required. Okay. So all
Yes,
the
sir.
best.
Please discuss about the timing issue also.
Yeah,
Please keep
sure.
that
So
in
I
mind.
will talk to the other instructors, and if possible, I will shift it to Sunday, right, at 8 p.m. Okay. Yeah. Okay, then all the best, everyone. See you next week. Thank you. Good night.
Thank you, sir. Good night. Bye.
Thank you. Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you.
Sir.